Yeah, so last week we already looked at attention and we went through the whole journey from sequence models to sequence models. And then we talked about the limitation of sequence to sequence models as it was in those days when we were using just the context vector, the internal meaning basically of what the sequence models were generating. Use our internal meaning to um, generate an output sequence. And we saw that there was a problem, loss of context, loss of information. So the output sequences that were generated that way were not that good. Okay. So researchers did more work and came up with the attention mechanism. Attention mechanism was a vast improvement because putting the attention mechanism in a sequence model allowed the decoder part of the sequence, the decoder output side of it, to basically directly look at the sequence that's coming in. And then that allowed the context vector to even be thrown away. Then we had attention mapping. And the attention itself was developed to a point where attention basically just worked on its own. Attention basically is saying for every element in a sequence, there is a way it affects every other element in that same sequence, right? And the meaning, how it contributes to the meaning of the entire sequence, right? And from there, we started having from that cross attention, which is the tension between decoder and encoder, what the decoder is generating on the encoder as um, consumed basically. We then had self-attention, which is a sequence on its own. And then the Google researcher decided to just throw away the uh, the sequence models from that you know they threw it away. They threw away the LSTMs, and we were just left with attention. And they call the attention is all you need. And that led to the transformer architecture, which is what the world seemed. So basically, almost all of the top models that are used for natural language processing, the large language models, which we are going to talk about today, they're all based on that simple principle of attention, you know, then you have a projection of the input into three different projections, right? The Q, which is a query, the K, which is a key, and the V, which is a value. And the query is saying, what do I want to generate next? What's the next token I want to generate? That's the Q. And the decoder that normally asks that question. And then the key is what is coming in, the input sequence. And then that allows the Q and the K are now, multiplied a dot product to give you the attention scores. The attention scores are then scaled and soft maxed to now give you the attention weights. So the attention weights is now a matrix of each element in a sequence against itself and others, right? Not just against itself, but against other elements in the sequence to show the weighting of contribution or coupling. If you think of it that way as coupling, the coupling between each of the words in a sentence, right? The words that are highly coupled will have higher weights. The words that are not so coupled will have lower weights. And those attention weights are then used to multiply to the value projection, which is still the same input sequence, but a different learning a different, basically what is the importance of each of the elements in the sequence. So importance plus times weight gives you um, the final attention value, which is saying, in fact, that will be like the final meaning of each of the tokens, right? In that sequence. Of course, I have shared a video, very nice video that explains this thing so well. So if you have not checked that video, just go to the channel on Discord and check it out. So that was a transformer, and we talked about different things. The transformer also has an encoder and a decoder, just like the sequence models. The only difference is that the transformer's encoder is just made up of fully connected networks. There isn't, it's just made up of the attention projection, then the attention matrix, which is, the most the heavier part of it. The attention matrix extracts the interrelationships or interconnections or the couplings, if you may, between the elements of a sequence, the words in a sentence, right? And then we now have an FFN, a fully what we call a feed-forward network, which is two fully connected layers that are connected, together. The fully connected layers extract the meaning. That gives you the encoder. And then the encoder is connected into the decoder. But the decoder, unlike the encoder in a transformer, um, has the inputs are masked. The attention matrix is masked, like we said, the upper triangular mask, to prevent the future parts of the sequence that the decoder is trying to predict. Remember, not predict, generate. The decoder always tries to generate, right? While the encoder is trying to understand the sequence, the decoder is trying to generate that same sequence or a new sequence, right? So that's why a decoder has a mask, a trio. It's a triangular upper matrix, right? And then um, apart from that, so the decoder has that, then the decoder also has a cross attention, the second stack of it. So it takes the query from itself, but it takes the key and the values from the encoder. And those are details of architecture. Basically, all of these architectures evolved over time, a lot of research, testing, and so on by machine learning experts over the years. And we now have that. So today, we are now going to talk about the specific application of transformers in large language models, right? Transformers can be used for almost anything, right? Most people think that it's only for language or natural language processing, but transformers have been used for other things as well. They've been used for vision, right? They call them vision transformers. We're not going to really look into that, but we talked a little bit about it when we're talking about CNNs, convolutional neural networks, right? Transformers have been used for game, playing chess engines, for example. Transformers have been used for any number of things, right? So they can solve problems where sequence matters, where there is a lot of interrelations, right, between the elements of a sequence, where it is complex, right? The interactions or interrelations between the data or the features are very complex and so on. That is, the domain of transformers. But here, when we talk about large language models, we're now talking about very specific use of transformers in the context of language processing, right? And as the name implies, these are very large models. It's not something that you and I typically will be able to train on a small Jupyter notebook. We have massive GPUs that are used for it. So we are going to look at that, and we will look at how we can train models, the principles behind it, and then fine tuning. And you now find that because large language models are very large, most times you do not start from scratch to train. You may not have enough data. You may not have enough compute, right, to be able to train from scratch. So you see that we have, what we call fine tuning. But we'll talk about pre-training first. Pre-training is, yes, when you're training the model from scratch, and their typical objectives, MLM and CLM. We'll talk about BERT and GPT architectures. We'll talk about tokenization, embeddings, and masking, which we've kind of already seen those already, but we'll delve into them. Then we'll talk about fine-tuning using LoRa and QLoRa, and then other ways of fine-tuning large language models. which includes prompt and instruction tuning. So first of all, what is a large language model? I've already kind of said it. Large language models are very deep neural networks, very large neural networks. Large, not really large, they're more like deep, plenty layers. Some of them have up to 1,000 layers, some even more, right? So far, we have not been training models that are more than maybe 2 or 3 layers so far. And by the time you do one that really has to have a good understanding, you might be talking about maybe a model that has 20 layers or 30 layers or 50 layers, right? That's still deep, but you can't classify that as a large language model. Large language models start from 500 and something layers and on. So so LLMs are basically very deep neural networks. So the first thing is the size of the network itself. The second thing is the amount of data that you train it on. It's mostly text data, of course. It's not numbers, it's text. But of course, the text has to be transformed into or encoded into numbers. And I think I showed that a bit last week, where how you translate sequences of text into numerical data, right? We'll look at those again, even though we have looked at it already. So, um, of course, LLMs, one of the key pieces of LLMs is that it's typically based on transformer architecture. Right now, there's no architecture that's better than transformer architecture for natural language processing. So most of the large language models, but all, I don't know of anyone, right, that is not based on transformer architecture. And then the large language models, they learn statistical patterns of language. That's really what it starts, where it starts. You give it a large corpus of data or text data, right? Massive. Just think about, hundreds of millions or billions of sentences or paragraphs or, pages of data. Most of this data is gotten from the internet, scraped from the internet and other sources. And you take them and you train them. You are not training them for a specific task, right? You are training them just to be able to understand language. That's why it's called a language model. You are training them to understand language. You're training them to understand the statistical patterns of language because language actually has patterns, right? There are patterns in language. If you pay attention to your own local language or any language that you understand very well, and you break it down, you see that there are patterns. We have what we call nouns, we have what we call verbs, we have what we call, adjectives, adverbs, articles, determine, what do they call them? Um, um, yeah, is it determinant or something, right? You have punctuation. You have, you know, the exclamation marks, the, question marks. You have clauses, you have phrases, right? So you have a lot of different patterns in language, and these patterns are not random because these patterns actually evolve from human communication, the need for human communication. And the human communication is not random. It's very specific. When you say something, you're actually trying to pass a specific message, even though there may be 10 different ways of saying that same thing, right? But you are passing a message. So effectively, human language has pattern, and neural networks are excellent at learning patterns, right? The only thing is that human language, the patterns are so complex. But on top of those patterns of language, we also have meaning. We have concepts. We have things that are being, transmitted in communication. So these large language models have learned not just to understand these statistical patterns, but at a deeper level to even extract the meaning and further extract patterns from the meaning, right? Remember when we're talking about convolutional neural networks, we're talking about the fact that um, each layer does a new level of feature engineering, and you have this hierarchical representation of meaning where a previous layer will extract, more primitive features. The next layer will extract a bit more refined features from the previous layer. and so on and so on. So if you have a lot of layers, at the tail end, the most, later layers of a model will be extracting very refined concepts. And that was in the context of vision. This same principle also applies with large language models, right? In the context of language. The early layers, the early encoders will be learning statistical patterns of words, sentences, what is a noun. It will be able to group words that are nouns and words that are verbs and the words that are adjectives and so on. But later layers will begin to take those, um, you know, syntactic grammatical concepts and extract even more complex concepts, phrases, meanings, right? Of course, you're already even passing the information as embeddings, which carry meaning. And what the attention matrix is doing in each of those encoder or decoder layers is it is essentially augmenting the meaning by looking at how the meaning of each word is affected by the words around it, right? So now think about that and then, you know, extrapolate it as you go deeper and deeper, to deeper layers of the neural network. It begins to pull even more complex concepts into even more complex concepts. So you will find that at the very deepest layers of a large language model, they begin to actually extract real meaning, real understanding of concepts. This understanding of concepts, if you want to, of course, you can represent them as embedding because that's what it is. Basically, it's multi-dimensional space, numbers that represent that, but it means something. And that is how these large language models are able to do these excellent things that we are doing. It is because at those very deep levels or layers, right, they are no more just looking at superficial concepts. They actually have a very um, in-depth understanding, if you may use the word understanding. I wouldn't use the word understanding because understanding goes beyond representation of meaning but further more than that. But let's just say that they have a very in-depth representation of the meanings of complex concepts. And then, so that's it. So these large language models are basically trained for that. They're not trained for specific task. They're not trained, for example, to be able to do one thing or the other. They're just trained to understand this language at a very deep level. That is what we call pre-training. So the idea of this was that if we could train models that are generic in nature in that manner, then if we want to now adapt it to specific task, we don't need to train from scratch. We just need some additional data that can refine that specific task, and they will be able to, you can train them on that additional data. So with that, we don't need to always train, a billion parameter models from scratch. Rather, we can take a pre-trained model. Training a billion parameter model takes time. Even with a lot of GPU, it could take you a year or 2 years or more. Some of the models that we are using now has taken years. Then imagine if you didn't have a GPU, right? Or you had a weak GPU. It could take, 5, 10 years. If you're using a CPU, it would take 500 years, right? To train these kinds of models. So that idea of retraining it for every single task does not work. It makes more sense. Train a generic model, right? And then fine tune it with much less data. So the beauty of it is that when you're fine tuning, you don't need as much data as when you're training because it already has, is rooted, is anchored on a lot of concepts. So that's the idea. So typically the pipeline is you do pre-training. Pre-training is self-supervised. So what do you mean by self-supervised? You are not really giving the you're not really in supervised learning, you are the one that prepares the X data that you give to a model and the why or label data that it uses to learn what to predict. Okay, that's supervised training. Unsupervised is where you don't even give it any Y data. You just give it the X data and it does clustering and is able to find patterns in the data that you have given to it. But self-supervised is what is working in natural language processing because you're actually giving it sequences of text. And I already showed us last week how you can then take from that sequence of text, you can generate training data where you are simply saying, take the first token, and then the next token, the first token is the X, and then the next token is the Y, right? That gives you one data sample. Then take the first two tokens, that gives you the X, and then the third token, take it as a Y, and that gives you another sample. Take the first three tokens as the X, and then the fourth token as a Y. So effectively, you can give it any sequence of text, and you code it in such a way that it generates its own training data, right? X always being n minus one tokens, while Y is the nth token, right? And you do that. So if you have if you have a sequence of length n, you are going to be able to achieve n minus one data samples from a sequence of length n because the first one always has to have something. So that think about that from one sentence, and if the sentence has 10 tokens or 10 words in it, right? You will generate 10 training samples or 9 training samples rather from a sentence that has 10 tokens in it. Okay. So now if you have a million sentences, then of different lengths, of course, the number depends on the length of the sequence, right? So if the average length of the sequence is maybe let's say 50 tokens or 50 words, and they are a million, then you can generate 49 million data samples. So you can see how that really helps with large language models. So that's self-supervised training, basically. It still gets its data from people, but you don't have to label the data for it. It labels its own data. And that's really the most scalable way of training models. Because the biggest bottleneck is when you have to have human beings labeling data. Data labeling is a big slowdown in training in machine learning because you cannot use human beings. So, for example, a Cipher 10, where you are labeling, images as cat, dog, aeroplane, and so on. It is human beings that have to do that, right? And that's why the interesting thing is that all of the capture and stuff that we used to do on the internet, when you go to log onto a site or something, they'll bring up some pictures and ask you to pick which of them is which. You are effectively actually labeling data for them because when you pick, right, you are picking data and you're saying this is a cat. Okay, pick which ones are cats and you pick. You have labeled it for them and they will use that data to train their models. Of course, if you mislabel them, that is still allowed because in training a model, some element of noise is even acceptable. In fact, it's even desired. So some small mistakes will be considered as noise in the training data. So that is self-supervised training. That's the first one, pre-training. Then you now do what we call fine-tuning or alignment. So fine-tuning is now you have a pre-trained model that is generic in nature in terms of being a generic language model, right? Then what you do is you then pick data for a specific domain that you want that large language model to specialize in and use that data to fine tune it. That's what we call fine tuning, to train it on that. That is fine tuning, right? And these days, fine tuning is a thing that most machine learning engineers do, right? Especially if you are doing it on your own, trying to figure out how to get a model to do something. So fine tuning is where you take a model that's already pre-trained, you bring your own data, and it learns and becomes really good, right? with that specific data. That is fine tuning. And then after that, you deploy. So that's basically how this works. Um, Examples, we'll look at some of the examples. We have BERT, GPT, Llama. So these are large language models. So let's talk about the steps in that pipeline. So the first step is pre-training. So the main objective of pre-training, we have two major ones, even though you could see that we have generally up to five, right? Let's talk about them. So the first objective is given the name MLM, Masked Language Modeling. In this case, you want your model to predict masked tokens. So what do we mean by mask? Is that upper triangular matrix mask that I mentioned earlier, right? And why are you masking it? You are masking the future tokens. So you are given, okay, sorry, it's not actually, you're not masking only the future tokens. You mask some of the tokens randomly. So this is one way that you train the model by using MLM, where you give it tokens, right? And then when you give it tokens, you mask some of the tokens, and then you ask it to predict those ones that you mask. We'll look at it in more detail, but it's something like saying, um, you tell somebody something like, the name of the boy is Dash, right? So the dash is the mask. And then you are asking the model to predict those dashes. So you of course do you have to that is generated still from the training data, the sentences, the words, and all of that corpus of text. Then the second one is the CLM, which is a causal language modeling. So in this case, you're asking to predict the next token in a sequence. Unlike the mass language where you are asking it to predict randomly any of the words in a sequence. We are going to look at it in more detail. So causal language modeling is this one you are predicting, you are training it to predict the next token. So the MLM has been used by BERT. BERT was the first language model, trained using that idea of attention is all we need, right? Um, Google was the company that did that. And then GPT came from OpenAI. So the main difference is that in MLM, it's what we call bidirectional context, where you can give it the entire sequence, right, without um, obscuring the future sequences or the future elements in the sequence, right? While CLM uses autoregressive, so autoregressive is left to right. In that case, you obscure the future elements and you only train it, you know. We'll look at it in detail. So those are the examples. CLM model predicts the next token in a sequence based on previous tokens. So this is like the standard thing that we have. And that's the primary objective for decoder-only models. So one thing is, yes, CLM is used for decoder-only models. We'll also talk about the difference between a decoder-only and an encoder-only. So GPTs are decoder-only models, while MLM is used for encoder-only models, right? Like BERT. BERT is an encoder-only model. And in this case, like I say, you hide random tokens in the sentence, and then you train the model to predict them based on the context. Then you also have other ways of training, pre-training large language models. Apart from the MLM, you have the span reconstruction. So in this span reconstruction, you actually remove consecutive sequences of tokens, right? Instead of just one or two tokens, you remove consecutive sequences of tokens and you train the model to predict those gaps that have been removed. Basically, this one trains the model to become really good at reconstructing um, missing information. Then we have PLM, which is permutation language modeling, right? So in permutation language modeling, you are trying to combine the autoregressive, which is the CLM, right, and autoencoding by predicting the tokens in a randomized order. Then you have contrastive learning, right? Contrastive learning is used for vision models multimodal models, basically models that go beyond text, images, videos, sound, speech, and so on, right? What you are trying to do is you train the model to understand the representation by maximizing the agreement between different augmented views of the same data, right? So those are the different ways, or when we say objectives, those are the different ways you can set up your training objective for the large language models. So let's talk about the MLM. MLM is used in BERT. BERT was one of the first language models that was, um, built and presented and unveiled to the world. BERT actually means the bidirectional encoder representations from transformers. So the idea of MLM is you randomly mask the tokens. So like in this case, you take this sentence and you want to use it to train the model. And the data, you have taken this is a single data point that you want to generate. And you randomly mask one of the tokens. And then you ask it to predict this other one. So remember when we're doing the other one, the sequential one, we always take the first X or the first N minus one, and then the nth one becomes the Y that it should predict. But in this case, we just randomly pick any value, any nth token, and we remove that one. That's the Y value, and then we replace it with a blank, right? And that blank is part of the X value, and that's what you want it to train on. So you are expecting that the model should be able to predict math. So typically, when you want to calculate the loss for this method, you use the cross entropy. Remember the categorical cross entropy. So you just calculate that cross entropy, but you're only calculating cross entropy over the masked positions. You're not going to count the positions that are unmasked because you don't expect it sees those ones. So you're not calculating loss at those points. You're only calculating the loss at the points where you remove something. So that's why the log P of xi, but only where the x is masked, right? Where the x is removed. So it's only the if it predicts correctly at the point. This is only these points or the tokens that have been removed that you use to calculate your cross entropy loss. So that's just it. And this is a sample code of it. So you see that the output model logits is output.logit. This is if you're using iTouch. And then we do a cross entropy loss. Okay. But this loss, you do a cross entropy, normal cross entropy loss function, but you're going to pass in mass position and then the labels of the mass position. So you are not calculating cross entropy based on all of the output values, right? Because you have the labels and you have the logits. The label is the actual Y value, while the logit is a predicted value. So you're not going to calculate the loss based on all the values. Rather, you only select the positions that were masked. So that way you're only calculating what the model is supposed to predict, which is the masked positions, not all the positions. All the positions you've already given it now, so it is expected I should get those ones right. So that's MLM. CLM is causal language modeling. So these ones are used in decoder type of transformers. Okay. For example, GPTs, GPT-2, GPT-3, right? This is the one that we kind of already looked at, where you are asking it to predict the next token in a sequence. So the input will be the first tokens in that sequence, and then the target, the Y value, will be what should be the next, right? And then when you're calculating the loss, you're just calculating it over the X, right? sorry, over the T, right? And because it's basically shifting the inputs by one, like we said, right? You're shifting, you always shift the inputs by one, and then you take the last one as a target. That's what is called teacher forcing, by the way. When you are training it, you are giving it the actual next value in the sequence as the the real value, the Y value that you should learn. So that's what we call autoregressive training, right? We didn't call it this name when we we're doing it, but that's what it is. It's autoregressive training. And it's still the same formula, right, for the loss. We are still using the cross entropy loss. The only difference is that the cross entropy loss always excludes the last value of X because the last value of X, um, sorry, it always excludes all previous values of X because in this case, we are taking X to mean the entire sequence, right? So at any particular timestamp T, you are excluding the first previous T minus one elements, right? In other words, anything that is to the left of T is the X. So we don't calculate loss against that. We calculate loss against the one that is T, which is the Y in this case. So this is also example of code. This one is not using PyTorch per se, but is using Hugging Face's um, framework. But Hugging Face's framework is actually built on top of PyTorch, but they add a lot of additional, really useful, helpful, functions. So, for example, auto model for causal LM already means it's a whole class that's been built for you to use for causal language modeling, right? And then you can get a model from pre-trained. This is basically you already have a pre-trained model, right? Hugging Face comes with a lot of pre-trained models, which you can get from their repository. And you can use this code to pull those models. And then you can fine-tune them by adding your own data. So in this case, the input IDs, remember when you are training, when we did last week, we showed that the input ultimately that you send into a language model is you pass it through an embedding layer. The embedding layer has an embedding matrix, which will convert the basically the IDs or the position of the words in the vocabulary. It will convert those positions into full vector embeddings, right? So the input that you always pass in are IDs. These IDs basically represent the where that word is in the vocabulary, right? So that's all you need to do. And then the labels will be the input IDs as well. So you're effectively giving the same sequence twice, right? But this model now knows how to exclude the previous values, right? The values, the previous the previous values in the sequence, right? It only uses the last one that matters. So you don't need to do a lot of the sequence preprocessing by yourself anymore. Just give it the words, give it the sequence. They've really simplified this to that point, right? And I think I should be able to show some examples of that. So those are the two, CLM, MLM. There are a bunch of others which we saw, but we're not going to go into detail. So this is an architecture of an encoder-based large language model. This is a BERT architecture. And remember, if you remember from when we're talking about transformer architecture, we said the encoder has two main sections, the multi-head attention and the feed-forward network, right? Of course, each of them have this skip connection and addition and layer normalization. So this is just normalization, like when we're doing normalization to reduce the range of the output numbers. Sometimes they become so large, right? So normalization helps to bring it, but you have to normalize it in such a way that you don't lose information. And that's why you're using layer norm. So, of course, we already know about positional embeddings, which kind of compensate for the fact that the attention that we are seeing here, there is three projections of QKV here. That's why I have these three arrows. These three arrows basically mean the QKV projections that go into the multi-head attention, right? And then remember, transformers don't have any idea of position or sequence, right? It is sequence models that know that. So the positional embedding is just a way to tag each of the inputs, each of the elements of a sequence that comes in the input to tag their position, so that there will be a difference between the cat, the um, the cat hits the dog and the dog hits the cat or something. The cat hits the dog and the dog hits the cat. Those are two different sentences, but they contain exactly the same four words, right? Or five words, which would not make much difference if you did not have positional embedding. So that's what positional encoding or embedding does, right? The word embeddings, remember word embeddings are essentially the vector representation of the words. So this come in the multi-head attention, which is just an attention, but you have parallel heads where each head can be used to represent different forms of relationships between the tokens in the sequence. Okay. So that's it, right? And then feed-forward network, remember I mentioned again, the feed-forward network is just two fully connected layers that are connected together, right? The only thing is that um, the size of the output from the first layer is a multiple of the size of the input, right? So it comes in, it is expanded, and then it goes out and it is squeezed again. So that's feed forward. So again, I know I did this already. You have two layers like this in the feed forward network, and you have an input that comes in, and then the output is like a certain fraction, right? And then but this is squeezed again back in. So for example, it means if you had an input dimension or embedding, right, the of maybe 5112, right? Then this one in between could be much more, maybe twice of 5112, 1024, or even 2048, right? Right. And then so the intermediate output is always much larger. That's what makes it helps with the representation of meaning. And then the output is squeezed back to the original size, which is 5112. So that's it. Those are always the two elements of an encoder. Okay. But of course, the other thing is that the encoder you have, this is just a single encoder layer. So in the bed, there were actually 12 encoder layers. There were 12 of these stacked up. So take note of that. There were actually 12 of these. There were 12 of these times 12. Right? There were 12 of these encoder layers stacked. So Yeah, so that's basically the BERT architecture, right? Now, but an interesting thing is when we're talking about the masking, this is how the masking happens. Remember, BERT uses MLM, right? Which is going to mask random um, you know, elements in the sequence or random tokens in the sequence. So for example, you can take this mask text as the input. The mask, anything you see mask here means it's being masked. The dash is hot, the dash are bright. You pass that in, and what you are masking is sun and stars. So this sun and stars become your Y values that you are using. You are training a model to predict, while the dash is hot, the dash are bright. Is this sequence forms the X for this specific data sample, and you train bet on that. It's as simple as that, right? After you have built it, you train it on that. So this kind of data is what is generated and is used to train it. Um, and that's it, right? If you have enough compute to train bets this way, you end up with a model that, you'll be surprised what they can do. So this is kind of more detail on the BERT architecture. The key features, it's a encoder-only transformer. It's bidirectional self-attention. So what we mean by bidirectional is that the encoder, the information you give to it, you do not mask future values. So because you do not mask future values, it is actually able to, if you give it um, the early parts of a sequence, it's able to predict the next ones. You can also give it the later parts of a sequence and it can predict the previous ones. That's the benefit of MLM, because MLM, you're not masking future parts of the sequence, you're just randomly masking. So that's what bidirectional self-attention means. It's able to do attention in both from the left to right and from beginning of the sequence to the end, and from the end of sequence backwards to the beginning, right? It uses MLM objective, and you have two special tokens. The CLS token, which is used for where there is a mask, and the SCP token that is used for spaces and other kinds of separators. So that's it. The architecture is very straightforward. You have a multi-head self-attention, right? Like we've seen here. And then with the add and norm, like I mentioned already. And then you have the feed-forward layer, which you see here, which also has its own bias add and um, layer normalization. So of course, this add is always taking a residual connection, the skip connection, from the input before the attention layer, right? And that is added. So this helps with the vanishing gradients problem, because it means a little bit of the input still keeps getting carried across. A little bit of gradient also keeps getting carried backwards, right? When you are training this model. So that helps to counteract the vanishing gradient problem. That's it. Still the same thing. We're basically just saying the same thing. It's the same principle, right? Now, this whole thing here forms a single encoder layer, right? And then you have n times of that encoder layer. So we already saw that BERT had 12 of those, right? But n can be any number. So you could do 5, you could do 10, you could do 20, you could do 100, right? Experiment with what you want. Now, this is basically comparing the bet with this. This one you see here is the complete encoder-decoder architecture that was popularized in that paper. That attention is all you need, right? But bet only takes the encoder side of it, right? It takes only the encoder side of this architecture. So basically, bet is just this part of it. That's what bet is, just that part of it. Okay. So if you look at it carefully, you find that this part of it is really what this is. You have the input embedding, you have the inputs, you have the input embedding, you have the positional encoding, then you have the projection, the QKV projection, right? You have the skip connection, add and normalization. You have the feed forward. Again, you have add and normalization. That's it. So it's just the encoder that is used for BERT. The next one is GPT. So GPT is the one that everybody kind of in recent times have become so familiar with. The GPT basically means the generative pre-trained transformer, right? The GPT uses a decoder. Uses a decoder architecture. It's a decoder only transformer and uses CLM, causal masked self-attention or causal self-attention, right? The basically in causal self-attention, like we said, the future elements or tokens in a sequence are masked. Okay, so you only allow the first elements of of the sequence into the decoder when you are training it. Okay, so um, it uses the CLM objective. That's basically saying the same thing. So what this does is it prevents the decoder, the model, from being able to see what is coming in the future, right? So it learns to generate or predict on its own, right? And that is what you can use to enable text generation. You find that encoder-only architectures are really good for classification, while GPT decoder-only architectures are really good for generation, for text generation. If you look at it, you find that this is basically using a decoder architecture in this two-layer architect, or in these two, this is using a decoder part of it, right? The most important thing you see here, these are two, looking at it, right? You have this whole block. This is a whole decoder block, right? You have a layer norm. So in transformer architecture, there are two different, apart from this original one that we had, where the layer norms, the add and norm, that the layer norm happens after each layer, right? You had the multi-attention layer and you had the norm happening after. And then also here you had the norm happening after the feed forward. There's also a slight variation where they put the normalization before the um, attention and before the feed forward. So that's called pre-norm, right? Versus post-norm. Those are two different ways. So in this case, what you have is a pre-norm where the layer norm is actually done before the projection. Now you have this projection here. You see how the QKV projections. They have multi-heads, right? Even though here it is represented as head one, head two, and head H. So this is actually multi-head. And each head goes through the same attention mechanism, right? Same QKV, right? So you have one head. This is one head with QKV, and then you have another head with QKV, and basically it just keeps going like that. So this is one head in a multi-head attention layer. This is another head, and this is another head. So basically, these heads are just copies of the same attention mechanism, right? If you look at it, you will see this whole thing that we talked about earlier on. You have the matmul of Q. This is Q and K dot product, then the masking. Because it is a decoder, you have to do the masking. So this masking is the upper triangular matrix masking that I talked about. And then you do the soft marks, right? And then you do the dropout. So here they added dropout, right? Before you now do the matrix multiplication with the V. So the V is this one that is coming in here. I do the matrix multiplication with it. And that gives you the final value of this is the attention score against the V, and you now get the final value of the process input that has attention imposed on it. And this is attention from one head. This one now gives you the input again, attention from another head. And then this third one is attention from a third head. And these three can then be concatenated, right, back into a single input. Remember here, they were actually split into three. So for example, if this layer norm, if this linear projected to maybe, let's say projected to maybe 33, 36, right? 36 outputs. Then you take 12 of those and put it in one head, take another 12 in the next head, take another 12 in the third head. So you have three different heads. And then, but when you come back here, you take those 12, 12, 12 and assemble them back into the same 36, right? Which then goes into dropout. So you can see that GPT has a lot of dropouts. Remember, we talked about dropout as being useful for regularization, okay? To make it more robust, to overfitting. Okay, so we still have the skip connection here, right? This is still the skip connection that comes from the input and is added to the output. So you can see that because we did a pre-norm here, we just do addition. There is no normalization again because we already did a normalization here, right? A layer norm. And then this is added and then this goes to the next full feed-forward network, the FFN, which also starts with a layer norm, first of all, right? A pre-norm. And then we now have the two layers that always make up an FFN. You have the first layer that is expanded out. Like I said, for FFN, you see that the output of the first layer is always like a multiple of the input, maybe times 2, times 3, times 4, sometimes even up to times, 5 or times 10, right? So that then is passed through a linearity here, basically an activation function. We call this GELU, right? And then it's passed through another fully connected layer that reduces it back to the original embedding dimension and embedding size here, which whatever it was. And then that's another dropout again to reduce overfitting. And then that is now added to the skip connection that comes from here. So you can see that it's basically the same thing, right? Just small internal differences. But interestingly, all these small differences count towards it. So this thing here you see is just one of these blocks, right? It's one of these blocks. This is one of these blocks, right? This is one of these entire transformer blocks. So with GPT, you have one, you have two, you have three, you actually have multiple layers. Just like with the BERT, right? This single transformer block is replicated multiple times and stacked on top of each other. It could be, 10, 50, 100, 500, and even more. And then at the end of the day, from the last encoder or decoder block, this is actually decoder blocks. From the last decoder block, you now have another layer norm, and then the linear, right? And then the softmax. The softmax is a probability distribution that will say basically this is the output that should be generated. This is the letter or the word or the token, right? That is most likely the correct token. And then, of course, if you paid attention, you also see attention. If you pay attention, that's the point. You also see that there was positional encoding and input embedding as well. So that's GPT architecture. Now, you can do a comparison of the two. The BERT architecture uses encoder, while the GPT architecture uses a decoder, right? So this is very interesting thing to note. And they both have advantages and disadvantages, right? There are advantages and disadvantages to both approaches. And there are places where the encoder architecture is best, and there are places where the decoder architecture is best, right? But the most important thing is that you use encoder architecture like BERT for classification task, where you want to understand something. So for example, if they say sentiment analysis, okay, we want you to train a model that can read, the um, comments from your users and then classify those comments, whether they are happy or sad, whether they are nice or not, and all of that. That's a classification problem. Okay. So it is best for you to use encoder architecture for that. Right. Um, Next word generation, that's generative task, right? So for task that is generative, generate a summary of whatever. If you read some you know corpus of data or corpus of text, maybe comments from your users or research or maybe a legal document, and generate a summary, right? That is a generative task. You are generating new text. That is a decoder problem. So the best architecture for you to use for that would be a GPT architecture or a decoder architecture. So this is kind of a simple guideline to help you decide what to use, right? Encoder architectures are good for classification. Um, Decoder architectures are good for generation, text. In fact, not just text, any generation, whether you're generating text, whether you're generating speech or whatever, right? So you find that most of the LLMs actually use a GPT decoder architecture. But interestingly enough, BET was the first LLM and they used encoder. It still did text generation, but it won't do as well as a decoder because encoder by its nature is designed to to come up with a meaning, an internal understanding of the sequence, right? It is not designed to generate a new sequence. It's designed to have an internal understanding of the sequence, right? So, but you could use that internal understanding to say, okay, based on my internal understanding, this is the most likely next word that it should generate, right? And that next word that it generates, it uses a probability distribution based on um, the vocabulary that you have, right? So you can actually use it, but these ones are far better when it comes to generation. So it's actually a good thing to know so that if you are doing a task, you can choose the right architecture. But interestingly, these days, only large language models, even with the GPT architecture, can also be used for classification, right? They'll be able to generate, um, because today's large language models have been, they're not just the bare bones plain encoder or decoder architecture anymore. There's so much scaffolding and stuff built around them that they're capable of doing much, much more. So this is a summary of the BERT versus the GPT architecture. Like I have said already, BERT is encoder only. GPT is decoder only. BERT uses the MLM, right? Which is the mask language model, basically masking random tokens to train it. While GPT uses CLM, which is a causal language model, basically what we call autoregressive, right? So it masks future tokens because you want to train it to generate. Context is bidirectional. MLM is always bidirectional. You are giving the entire sequence, right? But the GPT, you are giving it's left to right. You're only giving it the leftmost elements of a sequence at each time step. Bets or encoder only are best for classification, like I've said, while decoder only or GPT are good for generation. So, yeah, so this is self-attention versus mass self-attention. Like I said before, normal self-attention, every element of a sequence attends to each other, right, and to themselves. But in mass self-attention, the future elements of a sequence that have not yet been reached in that time step are excluded from the attention calculation, and only the ones that have been reached at a particular time step T are included in the computation of the attention matrix. So that's it for those. We'll do a little bit of hands-on, right? When we come back on Thursday. And what we are going to do, well, scale dot product attention. I'm not really going to go into all of this attention stuff because we have already done it before, right? So rather what I will do is we will look at the process that we normally go through when we are trying to when we are trying to prepare, basically the prep, right, of the data that you use for training models. So this is kind of summary of what we've said already. if you want to visualize, I'm now trying to give visualizations of everything that we have said so that it's easier to understand. Um, you can see that if you're doing bidirectional, bidirectional is MLM, right? Mask language modeling, right? So you have the L, which is a query. The L is the left-hand side, while then you have the V query, right? So in bidirectional, you give it everything, okay? In bidirectional autoregressive, you mask out some, right? Non-crossing is only the V and the L, right? Then in sequence to sequence models, um, you mask out the future on the L, right? This is um I think this is a bit difficult to understand, but it's just a kind of map of what is allowed, right? When you are in each of these different approaches. Okay, so when we want to train a model, you have to process the words, the sentences, the paragraphs, right? Those sequences that come in. Okay. So the first thing to understand, which we've said several times, is that the large language models, they operate on tokens, not words. Even though we have used words as a kind of proxy to make it easier for us to understand. And in the old days, a token basically almost matched the word. But these days, if you go take, if you go tokenize, you can actually check. There are some libraries we can use to do tokenization to see what they actually extract. You find that they're not really separate words anymore, but you know, it's based on the understanding of the concept. So it's a machine thing, right? But yes, we do have different kinds of tokenizers now that are currently used. We have the word piece, which is based on BERT. We have the BPE, which is based on GPT-2. We have sentence piece. So that's the first step. The first step is you tokenize. Then when you tokenize, right, those tokens are in a vocabulary. So the tokenization is not just going to give you the individual tokens that make up the words or the sentences or the paragraph, the sequence, is also going to translate those tokens. It's actually two steps. One is tokenization. The second one is indexing. Indexing is when you now generate IDs that correspond to those words. So you see IDs like this, these numbers, right? Last week I showed that these numbers basically um, are unique for each token. Each token has a unique number, and that number doesn't change. And that unique number of token basically is saying this is think of it like if you had a dictionary, right? And you were to give every entry in that dictionary, you give a serial number so that if I wanted to find a particular word, instead of me telling you the word to go and find a dictionary, I'll tell you a serial number of that word. I'll say, okay, go to this dictionary and check for the word 322 or the word 3562. You go to the dictionary, you're not going to go and look for the name of the word, but rather you go to the index, look for the number that's assigned to that word. And that is what, that's how you retrieve the word. That's what these input IDs are, basically. It's basically a representation of the position of a token in the vocabulary, from which that is extracted from. So this is the actual input that you would normally pass to a model because the models have an embedding layer that will now take this input. By the way, that embedding layer is correlated with the tokenizer. That's why tokenizers always have to be matched with the model. The embedding matrix has to use the same IDs as the tokenizer because the tokenizer is going to generate IDs, right? So the embedding model needs to be able to look at this ID and cross-reference and come up with the embedding vector that actually matches from the embedding matrix. And we saw that last week. So tokenizer, the inputs are then taken and passed into this. So this is how you can do tokenizer. If you're using the transformers library from Hugging Face, right, you can actually just import an auto tokenizer. So they have a tokenizer that just does it. You don't have to go through all the hard work anymore. You just do auto tokenizer, right? Then but the auto tokenizer, you have to pass a model that will be used for tokenizing. And that model is you can pick anyone. So in this case, birth based on case. On case means it is not case sensitive, right? Or yeah, it's not case sensitive. So you create a tokenizer, then you take that tokenizer, you can pass any sequence into it, any sentence, any paragraph into it. Like this case, transformers are powerful, right? And you will get the sequence of tokens from it, right? We're going to try this out. So after you have gotten the tokens, the next thing is the embeddings, like we have said. The embedding basically represents the embedding is a numerical, um, a list of numbers, basically, a numerical vector that represents the meaning of any word or sequence of words. In those days, we used to think, okay, one word has its own embedding, another word, but sometimes an entire phrase will have one embedding because the entire phrase has just one meaning to the LLM, right? Or even entire paragraphs can have just one embedding. That's how good these things are now. So it's effectively it's giving you the embedding is representing the meaning in that paragraph, the whole paragraph, what it has seen, its own understanding of it, right? So an embedding model is just another neural network that you pass in a set of objects, right? So first of all, I'm starting off by talking about text embedding, where you're passing in a sequence of sentences or paragraphs, and it gives you the meaning, right, as vector of numbers. But the interesting thing is that the when you generalize it, right, an embedding model can take any object as its input. So it's not just sentences or words. It can also take images. It can even take a speech, a speech waveform, or anything, and it will still be able to give you meaning. It has an internal meaning, you know, for that image and so on. So image, and that's how we're able to achieve what we call multimodal models. Models that you can give it an image and it can even generate the text for that image because that image has an internal meaning as well. It has an embedding. So there are different types of embeddings. You have the token embedding. So these are embeddings where you are embedding each token separately, right? They have positional embeddings. These are embeddings that are used to represent the position of the token in the sequence, right? And then you have segment embeddings. So the positional embeddings are the ones that you will now take and concatenate with the token embeddings to give the entire embedding. Then we have the segment embeddings. So Bet had this segment embedding, which was used to represent which segment in the sentence. So segments could be something like maybe paragraphs or chapters or something like that, right? So the final input representation is going to be token embedding added to or concatenated to the position embedding, concatenated to the segment embedding, right? It could be addition. Some people have used addition and others have used concatenation. I've actually seen both cases. Before, I used to think that embeddings was just concatenation because it makes more sense, right, to do concatenation. When I say concatenation, I'm saying appending them together in sequence. So for example, if the token embedding for something was a vector of numbers like 9, let me just, just 0 0.1, 0 0.3, and 0.01, right? This is the embedding that represents the position. Then the concatenation of another maybe 0.4, right, 0.14. Okay. Concatenation will be just add, append this one at the end. That gives you a new embedding, right? That's concatenation. But addition would be something more like uh you actually sum it, right? So this will now be 0.1 0.5 and 0.3, 0.44, and so on. So in both cases, I think people have used both, and well, it still works depending on your objective. So when you now do this, the final representation will be concatenation of the embeddings from these three, um, representing the word, the position of the word in the sentence, and the position of the sentence in maybe the paragraph or the chapter, right? So that gives you the final embedding, and that's it, right? So you can always get embeddings. You can check weights. You can check the shape of the weights, the embedding weights, and all of that. You will see that the embedding is always going to be something like the size of the vocabulary, right? When you're getting all the embeddings, and then the hidden dimension. So that is the second phase. Remember, the first was tokenization, where we split it into tokens with indexes or IDs. Then the next was embedding. You take those IDs and then you extract the full vectors that match those words. Then after that, the next is masking. Okay, so um, normally after embedding, right? If you want, if you can then take those inputs and put it directly into your multi-head attention directly if you are in an encoder. But if you are in a decoder, then you have to do masking, right? In fact, in today's LLM architectures, you just mask, right? So you could do it there are different types of masking. The MLM mask is for encoder where you are randomly masking out some of the input, right? But you give the whole input, but you mask out some of the elements of the sequence. Then you also have causal masking, where you mask out all future ones. That's for decoders or GPT type architecture, or padding mask, where you can add padding around it. So um, the causal mask, I think I mentioned this some time ago, is you use this upper triangular matrix. So you can see that the current value at time t is what is allowed for the LLM to see, but the future tokens are given zero. So the zero will mask out whatever embedding value existed there, right? So this is for the first one. Then for the second the sequence, we are now talking of the first word and the second word, or the first token and second token in the sequence. Will mask out the remaining, right? Here now we are talking about the first, second, and third in the sequence, and we're masking out the rest and so on. So this is the left to right causal masking, and you can see how we can achieve that. To get this matrix, this mask matrix, to mask out the future ones, you can either use the touch.trail, which is the triangular lower diagonal matrix, right? And just make the ones. So what basically this is doing is that anything on the lower side of this diagonal is going to have values of ones, right? And every other thing will have values of zeros. So it's effectively you start with a matrix that has zeros in it, but then you now make every value on the lower side of diagonal to be ones, and that gives you that matrix. So that can then be used as the mask. And this is still just a representation of this. It's basically the same thing, saying that, for example, the mechanism. So this is kind of intuitive in terms of when you look at it as the words, right? You have this word, dream big and work for it. This is a nice motivational thing, right? It has 5 words. So let's assume each word is a token. So it has 5 tokens, right? Dream big and work for it. Okay, that's 6 tokens. This is you could say this is the Q, and then this is the K. Dream big and work for it. But what we are saying is that when you're calculating the attention matrix, the future parts of this, when we are looking at dream only, right, we remove this other side. That's the masking. So then when we are looking at dream big only, we remove this other future part. When we look at dream big and we remove this, dream big and work, right? So that's so essentially what this attention matrix is now giving is only how each word attends to itself and the words that are before it. So here, dream is attending to dream. It is also attending, dream rather is attending to dream. It cannot attend to big and because these ones are ahead of it. Then big here is attending to dream and is attending to big, which is itself. But it's not attending to the future words because these words are ahead of it and work for it. And it's also attending to dream, it's attending to big, and it's attending to itself, right? But it's not attending to future words because these words are after and. Work, so that's basically the principle, right? Work is attending to dream, it's attending to big, it's attending to and it's attending to itself, right? And the future ones, it doesn't know about it. Same thing, the four also is attending to dream, right? It's attending to dream, it's attending to big, it's attending to it's attending to work, and it's attending to four. It doesn't know anything about it because it is in its future. That's the it that is supposed to be predicted, you know. And that's just how it goes. So that's the whole essence of that. It is this masking thing that is then converted into a matrix. This mask here gets converted into this matrix, meaning that anything that is one is allowed to attend, but anything that is zero is covered off, right? And that's really what this is. There's also, so this is kind of, again, showing us this is the attention layer. This is just the attention block. Again, you have the QKV, the Q and the K, you have the matrix multiplication, right? And then you have the scaling. So this will give you, when you do matrix multiplication, you're actually going to get this, right? And when you didn't mask, at this point, you've not masked it yet. So we're going to see everything. If you actually look very closely at this, is there you still see some things behind the mask. So you're going to see everything. The scaling will scale, and then you're still going to see values that are like decimal numbers, right? Then when you do the diagonal mask, that is when this gets zeroed. This upper side gets zeroed, right? And then you do the soft marks, and then this gives you the attention. The interesting thing is that this is diagonal matrix where you are just masking only the numbers on the diagonal, right? Because this one, you don't want things to attend to themselves. So you remove them. It's a cross attention. You only want to get the value of how each word attends to other words. So diagonal masking basically removes words attending to themselves. Yeah, and then after that, you do the matrix multiplication. So that's what this means. Okay, so that is how you prepare your uh, your your data, right? Before you go do the training. And I'm going to do some hands-on on that. I would have done hands-on. I'll do hands-on next week, right? But today I just want to, sorry, not next week, next Thursday. Thursday, I'll do hands-on. But I just want us to have an idea of all of the theory and what all these things mean. So we will look at all of this masking, preparing the data, masking, and all of that stuff. We'll do it actually with PyTorch, and we'll try to see, you know, how these things, appear, so that you have an intuitive understanding of them. But let's just look quickly at fine tuning. So remember, we said that training of large language models is of 3 steps. The first step is for you to train what we call pre-training, where you train it on just a large body of text data. All this while we've been talking about how you train it and some of the principles, the methods that you use to train it. So after you have finished training, it becomes what we call a pre-trained model. Okay. Now, after pre-training, it is not very useful for specific kinds of problems. So for us to use it for specific problems, we have to fine tune them. And so fine tuning is where you now take the data that is specific to the domain that you want to use the model for, right? And you now basically train that model. Yes, the model has understanding of language, very deep understanding of language, but how can I then apply that to specific problems? That's where you now use fine tuning. So fine tuning is what allows your model to adapt to a specific domain that you want it to, to be useful in, or you want to use it in, right? Fine tuning also reduces hallucination because you give it more concrete data and knowledge, right? Um, Fine tuning also improves what we call instruction following, which is where you actually train the model to follow instructions and do stuff rather than just predicting the next word, right? You can actually give it specific instructions and it does what you ask it to do. It generates output to match a kind of response to the instruction that you are giving to it. That's the benefit of fine tuning. And of course, fine tuning as an approach, it reduces compute because you're not training from scratch, right? If you want to train from scratch, that's crazy. The challenge is full fine tuning is expensive, right? Sometimes fine tuning may have a large memory footprint and there are billions of parameters for you to fine tune, right? So there are different approaches to fine tuning. Um, One of them is what we call PFT, parameter efficient fine tuning, right? So if you look at this image, it shows the pre-training is the original model. You have a large body of data, right? A large model, and then you train it, without any specific objectives. You just train it on data from everywhere and it learns on its own. It's like we said, self-supervised training. It generates training data from all of that and it learns, right? Of course, when you're training, you can do MLM, CLM, it learns to predict the next word based on those training objectives that you give to it. But after that, when you come to fine tuning, now what you are doing is that you now have a smaller amount of data and then you now take the models, you are only going to fine tune a few of the parameters. So in most cases, you will actually freeze the weights. You freeze the weights in a lot of, the parameters or a lot of the weights so that they do not change as you are fine tuning. But this is something that you have to do with a bit of experience and wisdom. And there are different approaches to it, right? Sometimes you could say, okay, let's just allow only a certain amount of change. Because when you're doing fine tuning, one of the things you need to avoid is if you over fine tune, you will lose the knowledge. Because remember, knowledge is in the weights. So you have to be careful when you're fine tuning that you do not end up, you know, um, essentially destroying the model, right? So let's talk about fine tuning. We have full fine tuning. Full fine tuning is essentially training the entire, fine tuning the entire model, right? But there's PFT, parameter efficient fine tuning, right? Parameter efficient fine tuning is a set of techniques, right? It's not just one technique. So what you are doing here is you are trying to adapt the LLM to specific task by updating only a small tiny subset of the parameters, not the entire model. Okay. If you're doing full fine tuning, you actually update the parameters of the entire model. Just update. You are not changing it significantly, right? But you are updating the entire model based on the small additional data that you want to fine tune it on, right? So in the traditional fine tuning, you are basically going to take the entire model, put it in a GPU, just as if you are pre-training it, basically, right? And then you give it this new data. You may freeze some of the weights, or you may, minimize the gradient. There's something we call, you throttle the gradient, or you, attenuate the gradients that go back into the model so it doesn't change or modify the model significantly, right? That will be full fine tuning. But with the parameter efficient fine tuning, what you do is that you do not change any of the original model weights. You instead create a new set of additional parameters, right? And then you now fine tune those ones, or you train those ones basically, so that they can effectively adapt the output that the model normally gives you to fit into what you want the model to give you, right? So the benefit of this PFT, or parameter efficient fine tuning, is that you are now able to significantly lower your computational cost, because you are not really going to update all the parameters in the model, right? It will reduce the GPU memory requirements, because you're not going to load all the parameters into the GPU memory, right? It's possible to fine tune large models on consumer grade hardware. The good news is that we can do it ourselves, and we don't need to write all the code, because the likes of Hugging Face and so on have already written all of this code that does the PEFT and so on. So all we need to do is just use it, and they have optimized it so that it works on consumer grade hardware. So PEFT will allow you to train your models faster, or fine tune your models faster, because you have fewer parameters to update. Training cycles are shorter, right? Then there's a problem of catastrophic forgetting, which if you were to train with full fine tuning, your pre-existing model weights or parameters that have already been trained can be messed up, and the knowledge in them will be lost. That's what we mean by catastrophic forgetting. So that's a very risky thing, but it can happen. So what you typically would do, you will freeze the original model weight. Freezing means that you mark them that they should not be changed, right? Think of it like when in touch there is a keyword that you use now. You say no grad, right? Touch.no grad or something like that. Basically saying this parameter should not be updated. Okay, so that's what you do. You freeze, and you avoid having to um, update parameters in the pre-trained part of the model. Is only the PEFT section that you have attached to the model that you now be able to update. Then, yeah, the output of PEFT training session is a tiny file, right? Even often in megabytes, not gigabytes, right? Because a massive model may be gigabytes, tens, hundreds of gigabytes. So think about that. Um, but a small model with the PEFT, you only have to train a tiny file that is kind of an adapter that you attach it to the larger model, right? So it is not the entire model you have to load into memory. It's not the entire model you have to load into GPU memory, right? It's easier to store and deploy. And then the other beauty of PEFT is that you can create multiple small adapters, right, that you can train on top of the base model. Each is optimized for a different kind of problem, or a different kind of task, or a different kind of domain. So that way you can just get one single model, right? Train multiple small PEFT on top of that small model. Sorry, on top of that large retrained model, and then you can have essentially multiple LLMs that can do different things, right? But only because the adapter, you have changed the adapter. Okay. So that's basically PEFT. Um so again, this is summary of it. In full fine-tuning, you update all the parameters, high memory usage, expensive for large models, 7 billion plus. It requires large GPU clusters, which most ordinary human beings will not have access to. But for parameter efficient fine-tuning, you can freeze a base model, you train a small subset of parameters, it's much cheaper and it's faster iteration. So these are examples of the PEFT, right? You have LoRa, right? Which is low rank adaptation. You have QLoRa, which is quantized low rank adaptation, prompt tuning, and then adapters. So we're going to look at all of those. And this is kind of process of a PEFT. Basically, you have the initial training phase, then you have customized dataset assembly, detection of key parameters, segment selection, fine adjustment process, performance assessment, and then progressive refinement. So the first of the PEFT methods is the LoRa, which is a low rank adaptation. So the idea is this. Um, you think of it this way. Let me use some graphics to help. Let's say you have a model that you have trained, a pre-trained model, and it's very large. And then it has an output. This output is just think of it as the output is a vector. And maybe the vector has a dimension of typically, let's think of it as just a flat vector. So it's going to give you a single output. Let's say that single output is 2048, has 2048 elements, right? So yeah, I have this long stack of a pre-trained model, and I have 2048. But this 2048 is not going to be very useful to me, mainly because the outputs I've not fine-tuned them, right? So the output it will give me for any given input will not really match what I want to do. So yeah, this is 2048 um, dimension output, right? So let's say I train it to generate words, or I trained it to, yeah, it can generate words, it can do stuff, right? The output is 2048 parameters. Sorry, 2048 numbers, basically. A single vector of 2048 numbers. Okay, but I want to train this thing. Maybe it can generate the next, let's say this is the embedding size that it will use to generate embeddings that are in a particular language, maybe English language or something. And I want it to be able to generate the next word in another language that's slightly different or a different kind of task. Okay. So what we now do with low rank adaptation is that we will add another model, another small layer or maybe layers, right? Another small layer or layers on top of this, right? And we now will train this. So we now create a new layer here. And this layer may still have 2048. Okay. Um, Ideally, what you would have done is you will have to maybe basically you're training an adapter to kind of adapt whatever vector that comes out here to another vector. It might still be the same dimension, right? Another output vector. So let's say 2048 also. But this 2048 now is trained on my own data. So it knows how to basically predict my own data. Now you find that the widths in this layer, the dimension of those weights have to be 2048 by 2048, right? Basically. So these weights here that will adapt, that's why they're called adapters. The weight of this extra layer that I am training, right? The this PEFT layer that I'm training here will have to be 2048 by 2048 because remember when we're talking about the weights, it's always the number of inputs times the number of outputs. So I'm going to end up with a very huge weight matrix here, right? This huge weight matrix is what will adapt the output of a pre-trained model that is 2048 to my own outputs that I have trained based on my own training data. Okay. But even this 2048 by 2048 is too much, right? So if you look at it, it may take a long time to train. Think of weight matrix of this size, it's huge. So what low rank adaptation does is that it now takes this W matrix and it decomposes it. Okay. So that's effectively what these numbers mean. So let me see if I can express it using these numbers. So what these numbers are saying is that um you have your weights W, right? This is W. So let me write it so that we can see. The original retrain weight is W. Okay. That is this one. Let me use a different color. So the original pre-trained weight is W. Okay. And that is this big one. I have trained it, or it has been pre-trained. So that's W. That includes this one anyway. So this output is still part of, all of this is part of one huge big weights array. Now, I can then train, um, so I can then train a delta W, which is the small additional weights, right, that I am training, right? One last layer. That's why it's written as W plus delta W to give me a new model that has weights equivalent. Just think of it that it is now equivalent to if I had pre-trained from scratch a new model that has weight W prime, which is the weights that would match my own output. Okay. So, but instead of me having to train this entire stack of W, right? Remember, this W is actually a stack of many layers. So there are many layers here. It's not just one layer. You could have up to 10, 100 layers, right? You have multiple layers, but all of them are just seen as a single weight matrix, right? Including these last few layers up here. So um, I now, instead of having to train another large one for myself, I train a small tiny, just one layer or maybe two, right? But let's just say just one layer that adapts this output to my own output. Same dimension, but the actual data that comes out from it, the actual predictions that come from this one matches more of my data that I'm training on than this. Okay. That's the benefit of, that's what PEFT means basically. Because when I'm training, I'm effectively locking this one, right? We freeze this. This is frozen weights. So frozen weight means that this previous stack, I do not update the weight parameters, I know, when I am training. I only train and update only this my own small section. This is the section I train and I update the weights so that I do not damage this one that holds most of the knowledge. Again, remember when we talked about hierarchical representation of knowledge, the earlier layers will have the more primitive representation, which the earlier layers are down here, but these later layers will have the more advanced, more nuanced, representation of knowledge. So I'm actually just stacking another layer to extract more features from this one that has more advanced, knowledge or representation of knowledge. So I'm actually going to get advanced, even more advanced, right? So it's easy for me to simply train a small layer with 2048 by 2048 weights matrix to have, very advanced representation of knowledge or idea of what is going on. I don't have to start from this low, earlier layers. But the problem is that even with 2048 by 204, it's still too much, right? The delta W, the weights, the new weights I'm adding, is still too much. So the low rank adaptation now takes this delta W and splits it into two matrices. That is what they mean by low rank. It actually splits it into two matrices. The delta W is split into two matrices, the A matrix, right, and the B matrix. And the A matrix is now going to have a lower dimension, right? and the B matrix is going to have a lower dimension, right? And this is a principle. So having understood this, I'm going to clear this out so that we can understand low rank adaptation. So let's say this, I am now looking at only my own extra adapter layer that I have added that has dimension of 2048 by 2048, right? So this dimension of 2048, which is still too large, what LoRa is saying, what the principle of LoRa, low rank adaptation, and what is represented in this thing is saying that if I have a matrix, right, W, that has dimensions of D by K, right, D by K, which is what you can think of this 2048 by 2048 as D by K. I can decompose it into two matrices that if I do a dot product, I'll get back this D by K. And those two matrices will be a matrix of D by R, right? Being the first matrix, right? And then the second matrix of R by K. So remember, if you do a dot matrix, a dot product rather, of these two matrices, so that means a B matrix, right, is R by K and the A matrix is D by R. So if we do a dot product of this, right, it's basically D by R, right, dot R by K is actually going to give you back the inner dimensions always disappear when you do a dot matrix. So that will give you back D by K, which is back to this. So we have done a low rank, a decomposition. So we now have two matrices, the A matrix, right, that has a shape of D by R, dr, right? And then we have a second matrix, the B matrix, right, which has a shape of R by K. Okay, so if we now select R to be extremely small, this double less than sign means R is much, much smaller than D, right? So in this example where my D is 2048 and my K is 2048, right? So for example here now D is 2048, right? And by the way, you can see that you can have different value of D and K. You can decide to um, train your model to the output size may be bigger than the original output size, right, of your main pre-trained model, but your adapter will have a higher dimension output or a lower dimension output. So I have a D of 2048. I also have a K of 2048. So if I now choose an R that is very small, very much smaller, let's say I choose an R that is let's just say 128, okay, or even 64, or even 32, right? Let's choose 32. Then we can now decompose this into two matrices, right? Where the first matrix A is now going to have a dimension of 2048 by 32. 2048 by 32. And then the B is also going to have a smaller dimension of 32 by 2048. So effectively, I have now decomposed a big matrix, 2048 by 2048, into two smaller matrices. Now, if you don't really understand the implication of this, let's bring a calculator and do some maths. So I'm going to bring in a calculator. 2048 times 2048, right? What's the number of parameters in 2048 by 2048? Let's do the maths. 2048 squared basically is well, this is 204 is 2 raised to power 20, sorry, 2 raised to power 11. So that's 2 raised to power 22, right? But let's do the maths. 2048 times 2048, right? That gives us 4 million parameters. So this would have had 4,194,304. So this your small model that, yes, it is not a 7 billion parameter model, right? It's not an LLM. It's not a 7 billion parameter, but it's a 4 million parameter model, right? That's the number of parameters you have to train your adapter. But with your LoRa, you now have two matrices that you can multiply and get back this four. But what is the dimension of each matrix, right? You can do that simple maths and you will see that um, your first matrix A is now going to have 2048 times 32, okay? So 2048 times 32, which is 65536. 65536. That's the number of parameters. You can see it's much less. You're talking about 65,000 as compared to 4 million. B is the same thing because B is just reverse of the thing. So it's commutative. So B is also 65,536. So by the time you add the two of them together, the total parameter count of the A and the B matrix, right, which is A plus B, is going to be A plus B parameter count is just twice of that, which is going to be about 131,000 and 72, right? So you now have two matrices A and B that have 131,000 parameters, as opposed to the original W matrix that had 4 million parameters. So you see the massive reduction in parameter count, the massive reduction in um, the memory size that you will use. That is what low rank adaptation is. So you can then take this, split this into two matrices, and then you train those two matrices, right? Basically is a dot product that you will use to recover back the original matrix, right? So you can now fine tune by fine tuning by training the A matrix and the B matrix, right? You now train low rank matrices. That's what it means by low rank. The rank is the R, which you choose a number that is so much smaller than the actual dimension of your input and your output. So you can see it as a decomposition of, think of it this way. I have taken the input, I have decomposed it, right, to a smaller I don't know how to sketch it, but let me sketch it this way, right? It is like saying I have taken this matrix and I have split into two matrices, right? Where this one is going in, right? Right. And then another one that is going back out to the original 2046, 2048 size. But these two matrices will be multiplied, dot product. That's what this already means. Delta W equals A dot B is a dot product, right? That is LoRa. So when you hear of LoRa, it is just a method that allows people like us that don't have such huge GPU computational capability to still fine tune um, large models, large language models, and use low rank. Because the thing is that most of the pre-trained knowledge, most of the knowledge that you are using, or that your model lens, your adapted model lens, is still coming from the pre-trained knowledge, right? The pre-trained model, the big stack that you remember that we didn't touch. That is this W is the main store of knowledge, Your own delta W is just adapting the W into your own specific domain specific data, but it's still too big. So you decompose it into AB. AB become the two low rank matrices that you train. And that's it. So it drastically reduces the number of trainable parameters. It helps to train your model much faster. And you don't have any latency increase in inference, right? And then later on, the interesting thing with this LoRa is that you can merge those two low rank matrices back into the base model. There's a way you can merge it by summing, right? By summing, so your pre-trained model actually becomes, a trained model, right? So LoRa is commonly used for the attention projection matrices, the Q and V, because those tend to be very large. Okay, so that's the principle behind LoRa. Um, this is just kind of a repetition of that. But the main thing is that this is a code that you can use. So again, you're not really writing the code yourself from scratch because Hugging Face has done it already. You just need to understand the principle behind it. So all you need to do is you get PEFT. PEFT, remember PEFT um, um, is fine fine-tuning performance enhancing parameter efficient, sorry, fine tuning. So you get PEF, parameter efficient being that, well, it's efficient for the number of parameters that you're using. So you can get your LoRa config. This is what you use to configure LoRa. Like I said, there are different kinds. We are going to look at a bunch of other ones. We have QLoRa and the rest of them, which we'll look at shortly. So, but you get your LoRa config, you get your PEFT model, which allows you to essentially create a PEFT model from a pre-trained model. So the first thing you do is you use the auto model for causal LM. Again, this is Hugging Face PEFT, right? Implementation. It makes it easy. So you take this auto model for causal LM, right? This is when you want to use a causal based training or model that has been trained based on causal, that's CLM, right? So GPTs, again, remember it's GPT. So we'll get a pre-trained model, GPT-2 that's already been trained. Then we now set up the LoRa configuration. We specify the R. So remember the R is the low rank dimension size that you choose. So you choose very low value. Here, I was even talking of 32, but here they choose R of 8. Okay, then you choose the hyperparameters. These are all hyperparameters, by the way. The R itself, the rank, the alpha, which is the learning rate for LoRa, for the LoRa adapter, the section of the model that you are training. Then you specify the target model modules inside this pre-trained model that you are going to target for training. So the C attention, you specify dropout. So if you remember when we're looking at this thing, we saw a bunch of dropouts here. When we're looking at the GPT model here, there's a bunch of dropouts. So there's dropout. It's good to do dropout because that helps with regularization. So that's it. You specify that. Then you use this get PEFT model. You pass in the original pre-trained model. Then you pass in your LoRa configuration. You're going to get a new model that already has the LoRa head or adapter attached to it. And then you can now do this print trainable parameters. This will tell you the total number of trainable parameters. And you can see it's just 0.2% of the total number of parameters. That's small. And you can train with that. So that's LoRa. This is QLoRa. QLoRa is just LoRa, same thing, but you now do quantization. So quantization is something that unfortunately I don't have so much time to talk about, right? So we'll talk about that later on. But I think I'll stop here and then on Thursday we'll continue with the rest. But QLoRa basically is you quantize a model 4 bits, right? That keeps the LoRa weights in higher precision, and then you use double quantization. So it's the same thing as LoRa. The only difference is that you will use a quantization configuration from it. So this one is used for Llama and a bunch of other models that are quantized. Yeah, so I'll stop here because we are out of time. When we come on Thursday, we'll do some of these things hands-on. I'll complete the rest of the slides where we'll talk about the other methods for fine-tuning your models, including prompt fine-tuning, supervised fine-tuning, instruction tuning, and so on. And then we'll do a few examples. So that's it from me for large language models and the methods that we currently have. Are there any questions?